which is e.g. what we call the trinomial joint PMF. So what is this? This is going to look like an extension of binomial, right? It's trinomial. So you consider an experiment, right? I'm going to use capital N, which is I've been using it in my notes, which I don't want to change, although it's more commonly written with small n, but doesn't matter. So n independent trials of an experiment on which you can get, let's say, 2 events, 2 exclusive events you have identified. So what I am trying to say is that you have identified two exclusive possibilities. For example, getting a 1 and getting a 6 on a throw of die, right? And you are considering n different trials of that. That is just okay, let me write it here, e.g. 1 getting 1 6 on die throws. So I am doing n trials. Now how will I define x and y? X is going to be the count of one of those events and y is going to be the count of the other events out of in n trials. So x by definition is the count of, let us say, event 1 and 2, say events, right, 1 and 2, count of event 1 and y is count of event 2. In n trials. So you have these 2 random variables defined in that manner. Clearly the space is discrete, right? Omega x and y can only take a discrete collection of values, a countable, in fact it is a finite collection now, okay. All right. So I wanted to keep it as general as possible, right? For example, in this case you could say x is the number of times you see 1 and y is the number of times you see 6. So now we are looking at the joint probability that the number of 1s is some number between, of course, 0 and n, and y is again another number between 0 and n, but the 2 numbers have some restrictions, right? The count of event 1 and the count of event 2 cannot exceed n. At maximum they can be n, they cannot become more than n, because if I throw die 10 times, if I right, I cannot ask for the probability of getting what is it, 7 1s and 9 6s. If individually I may be able to get 7 1s and 9 6s, but I cannot get them jointly, right. So this is, it turns out that this joint PMF arises in a number of situations, which is why I left it general. So this is one of those general, right, a general joint PMF, right, which I said we don't have too many examples of, but this is one of them. I am talking of a non-trivial joint PMF which cannot be obtained from, as we will see later, there is a very important subdivision where this operation can be done and when cannot be done. In general, right, we cannot do it, but there is of course a very important subclass where we can, we will come to that later, but this is an example where we cannot, as we will see, right. This fits into this. It's a very important note, once again I repeat, this fits exactly into this kind of situation where you know the marginal but you do not know the joint. How do I know the marginal in this case? Supposing I close my eyes to what is happening in y, then I look, if I look only at x, I will get the marginal PMF of x, right. I can always do that. Although the experiment will give me values of x and y, if I close my eyes to y, I can, if I look only at x, what do you think the marginal PMF of x is going to be on this? It is the success rate for binomial, Okay, now I want to be a little more careful here. I will say that event 1 has probability small p and event 2 has probability small q of occurring on any one trial, right. So, these two exclusive events, right, event 1 has probability p and 2 has probability small q, such that of course p plus q must be, let us say, strictly smaller than 1, right, not equal to 1. So, there is space for something else, neither 1 nor 2. And of course, p and q are both bigger than 0. Both of them can happen, but they do not tile the space, right. If they tile the space, then you really do not have much of freedom, right. Why if you say x occurred k times, then y must occur n minus k times if p plus q equals 1. It is like counting the number of heads and number of tails on just on a coin throw. There is no point in defining a y in that case, because you know the value of the number of tails. Why would you want to unnecessarily define a random variable for that, which is when you know the, right, when it is not really, I mean it is y. So, what I am trying to say is, knowing x you cannot, we will come all to this much later in great detail, but at this point you should just keep in mind that knowing the value of x, you really do not know exactly the value of y, right. That is also one very important thing about these joint distributions, right, in general, right. So, these two have some independent some degree of freedom. Okay. Now, let us look at the joint PMF of x and y. How would I write it? First step is omega xy. Identify this. Okay, x and y can individually take values from 0 to capital N. I have put capital N. I am going to stick with this earlier we may have used small n, but for now I am going to for this thing please, right, stick to I mean I am going to use capital N only. So, what is omega xy? The set of all points ij such that I and j are both between 0 and n, but you also want to do what? Say what? You want to say I plus j must be small, less than or equal to n. Of course, they can equal n, that is right. This is just I plus j equals n is possible, but not more. So, what kind, if you plotted all these points on the xy plane, it would be what? It would be a triangle actually, right? A triangle bounded by these straight lines, I greater than 0, greater than or equal to 0, j greater than 0, right. So, if I want to draw it like this, I would get something like this. So, what would be this line? This would be the line I plus j equal to n. You can do it like this, I j, right, and it is all these points on a nice grid like this. Isn't it? Okay. Just to give you an idea, this is the point n0, this is 0 n and so on, and you have 0 0 here. Okay. So, this is the set of points omega xy. Now, we want to ask again the same old question, what is this joint probability Px y I j, which is the joint probability x taking the value I and y taking the value j on a single run of the experiment, which gives you x and y the values, right. How would you go about writing this? Remember, x measures the count of event 1 which happens with probability p, and so in this straight away you are saying that x occurs, that is event 1 occurs I times, event 2 occurs j times. That is what we are saying, right. and neither occurs n minus I minus j times. So what do we have here? So this is going to be, it is going to have this term p to the power of I q to the power of j 1 minus p minus q to the power of n minus I minus j. That is going to be a term, right. This is going, what is this a probability of? This is a probability of a particular sequence of I times getting count 1, j times getting, sorry, I times getting event 1, j times getting event 2, and n minus I minus j times getting neither of them, a particular sequence. How many such sequences are possible? The number of times such events are possible will be n choose I multiplied by n minus I choose j. This is together called the trinomial coefficient. And what is, if you expand it out, what do you get? Okay, so let me say here clearly one more time, event 1 occurs with, these are probabilities, right, of events 1 and 2 occurring on any trial, and you are running experiment for n trials, and this is the joint probability that you get I times event 1 and j times event 2, and that instead of writing all that in English, we are writing it compactly like this. So what is this trinomial coefficient? You can clearly see this will be equal to n factorial divided by I factorial j factorial into n minus I minus j factorial, right. It is another way of, right, n factorial by I factorial, that n minus I will factorial will cancel, you will get exactly this, just a j factorial here, n minus I minus j. So basically that is all we need. So in the case of 1 and 6, getting 1 and 6 on right rows, p will be equal to 1 by 6, q also will be equal to 1 by 6, right. But I do not have to have 1 and 6, I can have 1 4 and I can have a square, and I can get whatever 5 square and 5 6 here or something, right, or that also will be equal, or whatever, I can have square here and only 6 here, whatever, I do not have to have p equals q obviously, isn't it? Okay. Now we have already said that the marginal PMFs, okay, so by elementary reasoning or whatever, by prior reasoning or whatever you want to call it, we have said, what have we said? X is binomial with parameters n and p, y is binomial with parameters n and q. We want to now derive these two marginals. So these are the marginal, we just call them marginals, marginal PMFs. How do we derive this from this joint? It is actually easy to do. All you have to do is make sure that you add the, right, add the, you take a particular value of x such as I, some whatever, some any I, right, what would be the limits on y? It would go from 0, given that you are adding for this particular value of x, you would go from 0 to n minus I. So to get this answer, so we check. In this case, pxy of k I comma j, what will be the limits of I and j? Sorry, j. J will be going from 0 to, I just now said can do this and check for yourself that it will magically come out correct or not so magically. Maybe note that this summation is only over j, which means that the I can be the j p power I can be pulled out. This n choose I also, so if I write it like this n choose I can be pulled out. So it's you can start from this version with which are two different combinatorial terms, pull out the n choose I and leave the n choose j, I choose j. So let me just do this just to I am just writing it inside. So what do I do here? This guy I can take out, this guy also I can take out. So therefore this is n choose I p power I. What do I have inside? I think this is easily summable. This is a very simple binomial summation. What do you get when you do this? So it is 1 minus p minus q plus q whole power n minus I, right? It is a simple binomial summation, is it not? So q plus 1 minus p minus q whole to the power n minus I, that is all it is for all I. Does not matter. For I equals 0 also it is true. So and I equal to n also it is true. Any n any I it is same summation holds. So what is this? Binomial. So it works. Where do we put a tick mark? Here? Okay. So particularly simple, simple but at the same time it's right, it also shows how the combinatorics exactly falls in line. That is what we have to keep in mind, right? The combinatorics always should fall in line. If you do not get this, then something is wrong. So, right. Similarly, I mean there is no point in doing for you can, I mean all you have to do for py of j is just switch things around and it should come automatically. Right. So this, that is why you have to understand clearly the region omega xy where the non-zero probabilities are concentrated, right, and it is not a area, it is basically a set of points in a discrete case. So if x and y are jointly discrete, they must be individually discrete, they cannot suddenly become continuous, as we will see. Continuous random variables will come to later. So x and y are jointly discrete implies that x, right, x and y jointly discrete, that means in other words they are described in terms of a joint PMF. If they are jointly discrete, they must be individually discrete. In other words, a set of values that individually they can take is also countable. So all these discrete random variables therefore fit into a nice pattern of points. In the few minutes that are left today, I will look at another application of this trinomial PMF, right, another situation where it happens. Supposing you are throwing capital N balls into some m bins. This n, unfortunately, or whatever I have to keep it, right, the same as capital N, right. This happens when I write notes in two different places, and one place I have used capital N and small n, but I can't do it on the board, right. So I have to synchronize. So if I have to, right, throw them, and these bins are distinct, in other words they are numbered 1 to m, you know exactly, right, which bin a ball has fallen into, bin number 1 as opposed to bin number m. So what is the standard assumption you make here? Each ball can fall into any of the bins with the same probability, right. So any bin with equal probability, right. Oh. And if you want, you can have the balls as numbered or not, it does not really matter, because ultimately what are we going to do? We are going to count the number of balls that have fallen into any one of these bins, right. Just compare this with the number, getting the number of 1s and 6s. By throwing a die n times, you basically created how many bins? You have created 6 bins. That is all. Here I am generalizing to m bins, and I am just saying ball falling into any one of the m bins with the same probability, which is 1 by m here, and each throw is independent of any other throw. Throws are independent, which means probabilities just basically multiply out. So how do I define x? X, for example, by definition is the number of balls in some bin I, the ith bin, or let me write it like this, ith, I dash th bin, right, and y the jth. J obviously is not the same as I. Do you not get back exactly the same situation that we had earlier, except that you do not have P equal to Q, you have, sorry, you do not have P and Q is different. So P and Q are both equal to 1 by m. Otherwise this is identical to that. Not only that, I can actually look at more bins also, like we could do for the die rolling. You can have a larger collection of random variables, but since we are restricting this discussion to 2, I am just looking at 2 bins, 2 different bins, right. Okay, so let us quickly recap this the trinomial PMF that we looked at the end of yesterday's lecture, right. Let me see, has he started? Okay. Okay, so we did this, we looked at this yesterday. The P and Q are the events of, right, are the probabilities of the 2 events which are exclusive, and P plus Q must be also smaller than 1. Right. It turns out if you make P plus Q equal to 1, it becomes trivially binomial. I will leave you to think about that, right. I am not going to look at that special case here, right. It turns out that this will reduce to that is y will become n minus x or something. You can go and think about what happens if P plus Q equals 1. Okay, so so we are assuming P plus Q is strictly smaller than 1. Okay. So where did we see this in action yesterday? E.g., I will come back to this example, which is occupancy, right, an example of occupancy, which is n balls. Did I call them bins or cells? Bins. And then y, of course, the jth. So this implies that P will be equal to Q will be equal to 1 by m. So this is by itself an interesting probabilistic situation, right. You may have studied this in statistics somewhere. Does anyone recall what kind of statistics this refers to? Some Maxwell-Boltzmann some other, this is one of those kinds of things, right, where any particular bin can take can take any number of balls, right, any of the bins can take potentially an infinite number of balls, but we do not have that many, we have only capital N balls. Anyway, so but there is a different type of statistic when each bin can take maximum one ball or something, so that all these come under those types of situations, right. So that is why I wanted to bring that, and here of course we are specifically looking at this situation of x and y being these two random variables, then you get exactly the trinomial PMF. This is more general than this because here I am allowing P and Q to be two different numbers, they do not have to be the same. If you for example club some of the bins out here, instead of saying ith bin, right, how do I make this P and Q different? Even here I can club the bins, right, I can say x can be the count of the balls in the some let us say the kth and the lth bin or something, right, and then y can be the ball, it can stay as it is. So in that case P can become 2 by m and Q will stay at 1 by m. So it is even here it is possible to have different P and Q depending on how you define x and y. Anyway, so let us keep moving on, right. Okay, so instead of spending more time on this example, we will come back to it later. And okay, one last thing I wanted to again recap was that the joint to marginal, right, this is all obtained by just summation Px of x if you do this for the trinomial case, we checked it yesterday, what did we get? So trinomial gives you binomial. Right. So this calculation has to be repeated separately for all x in omega x. In this particular thing it was easy to do because the sum you had to do only one summation and this, the I did not matter, right, whatever I you had the same summation held, but in general you may have to sum differently, but does not matter, it is still doable.